Welcome to today's Explainer. Have you ever stopped to think about how the internet actually, physically works? Like, how are entire continents connected, and how do these massive data centers process unthinkable amounts of info in literal milliseconds? Well, you're in exactly the right place. Today, we're diving into the physical backbone of modern networks, the wild and fascinating world of fiber optics. We're going to look at the raw technical blueprints, pit single-mode and multi-mode fiber against each other to see what they can really do, and break down exactly how light is manipulated to, basically, move the digital world.
Okay, let's take a quick look at our roadmap for today. First, we'll cover the limits of light, then multi-mode fiber capabilities, followed by single-mode fiber capabilities. Fourth, we'll hit ISO fiber performance standards, and we'll wrap up with real-world network use cases.
So, Section 1, the limits of light, understanding optical constraints. Before we even try to compare the cables themselves, we really need to lay down the universal rules of light. You see, when we transmit data as pulses of light through glass, we are essentially fighting against physics. The first constraint here is attenuation, or loss. This is just the natural signal weakening that happens as light gets absorbed or scattered by the glass core over a distance, and we measure that in decibels per kilometer. Now, a lot of people just assume this natural fading is the biggest hurdle stopping us from sending data further. But interestingly enough, in modern high-speed networks, signal loss actually isn't your primary enemy.
Right, so the crucial point is that your real enemy is dispersion, specifically something called pulse spreading. Imagine a clean, super sharp pulse of light traveling down a fiber. That represents a binary 1. As it travels, it starts to spread out. And if it spreads out too much, it literally overlaps with the next pulse, which completely corrupts the data. It's a mess. Dispersion is the ultimate differentiator here. It basically dictates the entire engineering design of modern fiber networks.
All right, moving to Section 2, multi-mode versus single-mode, the tale of two fibers. Let's look at the macro to micro difference between the two main technologies engineered to manage these physical limits. On the left side, we have multi-mode fiber, or MMF. This uses a relatively wide core, usually 50 or 62.5 microns. And because it's wider, it lets us use cheaper light sources, like basic LEDs or specialized lasers called VSOLs. Now, contrast that with the right side, single-mode fiber, or SMF. This acts as a tiny, highly precise pipe. Its core is incredibly narrow, just 8.3 to 10 microns, so it requires a highly focused, and definitely more expensive, precision laser to inject light into it.
To really grasp why these different core sizes matter so much, we have to look inside that wider multimode core. Because it is wider, it allows multiple modes or paths of light to travel all at the same time. The light ray traveling perfectly straight down the center, which is the lowest mode, gets to the destination faster. But meanwhile, the higher modes are bouncing wildly off the outer cladding. They're essentially taking a longer, zigzag path, so they arrive later. This gap in arrival time creates chaotic pulse spreading. That is modal dispersion in a nutshell, and it forces some pretty massive distance limitations when you're trying to push high bandwidths. But single-mode fiber, it physically prevents that bouncing entirely. Because the core is so impossibly narrow, it only allows a single, fundamental mode of light to propagate. It just travels straight down the middle. What does that mean for us? It means there is absolutely zero modal dispersion. And because SMF eliminates that chaotic bouncing, it can achieve practically infinite deterministic bandwidth over staggering distances. We're talking 10, 40, even 80 kilometers or more, literally limited only by the electronics sitting on either end.
Next up, Section 3, the blueprint, ISO fiber performance standards.
So, having covered the physics and the core differences, let's decode the raw technical blueprints. To standardize network design, the industry relies on ISO ratings. Let's track how multi-mode grades have evolved, from OM1 through OM5. You'll notice a massive leap in bandwidth capabilities here. We start with legacy OM1 and OM2, which use those thicker 62.5 or 50 micron cores and basic LED light sources. They max out at very short distances for 10 gigabit speeds. But then look at OM3 and OM4. These are the modern data center baselines. They are laser optimized for those VCL light sources, meaning a 100 gigabit signal can travel up to 100 meters over OM4. Pretty huge jump. And then we get to the absolute latest innovation in this space, OM5, or wideband multimode fiber. What makes OM5 a total game changer is a technology called shortwave wavelength division multiplexing, or SWDM. So instead of needing multiple pairs of fiber just to send massive amounts of data, OM5 is optimized to send 4 distinct wavelengths. Think of them as 4 separate colors of light, down a single fiber pair, between 850 and 950 nanometers. This dramatically cuts down the physical number of cables you need in a dense environment. It effectively wipes out cable clutter while still effortlessly pushing 40 or 100 gigabits.
Now, shifting gears over to single mode, the standards are a bit simpler, but man are they powerful. Here we're comparing the legacy OS1 standard against OS2. Legacy OS1 was built for indoor use, and it suffered about 1 decibel of signal loss per kilometer. But OS2? OS2 is the definitive modern standard for long-haul outdoor networks, and it boasts a microscopic 0.4 decibels of loss per kilometer. The real genius of OS2 is in its chemical engineering. It's known as low-water peak fiber. See, in older glass, microscopic water molecules that got trapped during the manufacturing process caused a massive spike in signal attenuation right at the 1383 nanometer wavelength. OS2 fiber is engineered to completely remove this spike. That effectively opens up the entire optical spectrum from 1260 to 1625 nanometers, and the result? Engineers can use dense wavelength division multiplexing, which is basically shooting dozens of different colors of light down one microscopic pipe, multiplying a single fiber's capacity to just mind-boggling levels.
Moving on to Section 4, Visualizing the Traffic, Real-World Network Use Cases.
Let's bring all these raw specs to life and see where they actually live. Our first zone is the data center east-west fabric. This right here is the domain of OM4 and OM5 multimode fiber. The entire goal here is low latency, massive bandwidth between servers. Visually, you can think of this environment as pristine, dense, and perfectly orderly. We rely on multimode to handle a really chaotic, explosive pulse of 100 to 400 gigabit data. Imagine a rapid, pulsing ripple of cyan and green light. Because we're contained within short, cost-effective distances, always under 550 meters, multimode is the perfect, highly efficient tool for this sprawling, meshed grid.
Now contrast that with our second zone, the ISP backbone and cloud core. This is the exclusive domain of OS2 single-mode fiber. We use this to connect massive data centers to the public internet, or to link entire regions across continents. The aesthetic here is totally different. It's sleek, futuristic, cold, and silent. Inside that microscopic core, the traffic is just a single, laser-thin, focused, neon-white data stream. It travels thousands of kilometers, cutting right across oceans and continents, moving immense global intelligence with virtually zero loss and absolute precision.
But ironically, down at the enterprise access layer, which is the very edge of the network where you and your devices actually sit, we don't use sleek fiber at all. This is the SOHO boundary, small office or home office. It's a gritty, heavy, and chaotic world of standard unshielded twisted pair copper cabling, like Cat6a. Why? Simply because we have to prioritize power over Ethernet or PoE. Fiberglass cannot carry electricity, so we're stuck using heavy red and blue copper conduits to deliver DC power to things like VoIP phones and security cameras right alongside those pulsing cyan data streams. This gritty copper layer does all the heavy lifting locally before handing off the data to that silent, high-speed fiber backbone just down the hall. Which brings us to a really fascinating question to wrap up today's explainer. We've just seen the unbelievable scale of single-mode fiber crossing oceans and the sheer density of multi-mode in the data center. But at the edge, we are still completely tied to copper to deliver power. So as data demands continue to explode into the terabits, will the silent, limitless reach of optical fiber eventually force us to find new ways to power our devices, replacing that gritty copper access layer entirely? It's kind of the ultimate engineering challenge for the future of our physical networks. Thank you so much for joining me as we explored the scale of light. I really hope you found this breakdown as fascinating as I do.